This is the solution for the most frequently missed problem on homework 10, the one that said it was homework 13. That was about the contact forces in problem number 5. There were two boxes touching each other, and the big box on the left was the one that was pushed. And you had to find the normal contact force in between them. So please take a look at the solution to see if you can improve how you do this work. I start off looking at the system as a whole. So I have a funny shape here because I'm pretending the 110 kilogram box and the 75 kilogram box are a single object with a combined mass of 185 kilograms. That way the applied force is applied to everything at once. I don't have to worry about the contact force to start with, and I can find the acceleration of the system. So I label the vertical forces as well as the horizontal forces, and I'm allowed only one object in a free body diagram. So that's important. You got to be careful with that. I have some subscripts that S stands for system. So this is the normal force on the system as a whole, friction on the system as a whole, and that's the mass of the whole system. So when I come down here, I write sigma F or MA equals, and right there I've got the same subscript, MS, that I had up here, and I'm listing the same force labels. So I have FS and FA because I'm interested in what's happening in the horizontal direction. The other two forces are going to be balanced. So this is in the X direction. So when I do that, I plug in 185 kilograms because I added these two together. So that's the mass right here. And friction is mu times the normal force. In this horizontal situation, the normal force and mg will be the same. They'll be equal and opposite to each other. So here's mu, given in the problem. Here's m, that's the addition of the two masses together. And there's g. So friction becomes mu mg in this horizontal situation with no extra vertical forces. And then I add the applied force of 730. That's a positive because in my picture it's to the right. Friction is negative because in my picture it's to the left. To solve for acceleration for the whole system, I'll just have to divide both sides by 185 and use my calculator. And when I do that, I get 2.4 something meters per second squared. I'm going to use that in my other calculations. I want to keep it unrounded as long as I'm doing calculations with it. So that's how we begin. First, find the acceleration of the system. And you can find that as an example in your notes also. That idea that we start off getting the acceleration of the system. I then have to do a second free body diagram. A lot of people didn't do that. This problem needs at least 2 free body diagrams. Depends on how you work it, which ones you need. But in this step, I'm going to look for the force on the second block, the one to the right that has a mass of 75 kilograms, and it's being pushed by the first block, the 110 kilogram block. So I didn't feel like writing 110, so I just wrote the force of block 1 on block 75. There should be no numbers in a free body diagram. Hear that? No numbers in a free body diagram, unless it's the name of the object, and here I'm using it for the name. So there's friction on the 75 kilogram block, and there's my mg and my normal balancing each other. So when I write this net force statement, I have M75, so it would be good if I put M75 in my diagram so those things match, times the acceleration, and I'm going to make this one negative right there, and this one positive right there. So when I come down here to do mass times acceleration, I remember that the acceleration of these two blocks, because they're touching, has to be the same. And it's also the same as the acceleration of the whole system. So right here, I'm going to use this 2.4759 calculation. And then here's friction, mu mg again, but this time the mass will be just the 75 kilogram mass. We make a free body diagram and call it free because it has just that one object in it. And so all of our calculations are just based on that one object. And then this is a contact force that I'm hoping to find, the force of 1 pushing on block 75. So when I plug the numbers in, there I am using the acceleration again. The mass here is only the 75. They both have the same kinetic friction. There's the mass of the 75. There's 9.8, so here's mu mg, and here's my unknown contact force that I'm solving for. So when I put that on my calculator, I get 295.9. So I could be done with the problem at this point. I have found the normal contact force. That is the force of 1 pushing on 75. Now, a number of students kept going because they thought they had to calculate a different force. Remember Newton's third law. If 1 is pushing on 75 with 296 newtons of force, then 75 is pushing back with 296 newtons of force. But let's prove that and let's check our work, because you may have chosen to instead try to find the normal contact force by working on the first block, the biggest one, the one with a mass of 110 kilograms. So if you did that, it had 3 forces on it, because not only did it have normal and the weight in the vertical sense, it had the direct applied force, it had friction in the opposite direction, but it also had the little block pushing back against it. Okay, so we're not going to use that as we just calculated it. We're going to try to calculate that as if we don't know what that is. So here I go with sigma F or MA equals, I list all 3 horizontal forces. The ones to the left are negative. The one to the right is positive. I use the acceleration of the system once again. I use only the mass of M1, the 110 kilogram mass. Here's my mu mg. One more time, it's negative. And here's my contact force. It's negative, that one right there, my unknown. And here's the 730 given to me in the problem as the applied force. When I get out my calculator, I get 295.9 again. You can see tiny differences in rounding error here, right? This one in the hundredths column has a 5. This one in the hundredths column has a 4. But, sorry, bell ringing here, but those are the same. So what we've just demonstrated is what I've been telling you is true, because Isaac Newton taught us that it's true. The contact forces of 1 pushing on 2 have to be equal. By Newton's third law, the force of 2 pushing on 1 will be the same. So that's the solution to problem 5 on homework 10, the one that claimed it was homework 13. I hope that helps.